So happy to see a lot of people here. Let's have a special session of Built Integral Systems seminar with our guest Maria Matushko from Kirillov Institute about R-matrix Lax pairs for Calogero types BCD.
Thank you very much. And I will start with a short plan of my talk. So, firstly, I will give you some elliptic function notation. Then I will talk about the Calogero-Moser system, elliptic Calogero-Moser system. And the Krichever Lax pair with spectral parameter for it. It's type 3. Then I will tell you how to construct R-matrix Lax pair for it. It means that the elements of this Lax operator will be interpreted in terms of R matrices, Baxter-Belavin elliptic R matrices. Then I go to the BC type. This model is called Calogero-Inozemtsev model. The Lax pair for it is also known. Lax pair due to Takasaki. And then I will tell you how to generalize this Lax pair in terms of our matrices. Elliptic R matrices. This is our joint work with Andrei Zotov and Artem Maslovsky. And I will add that to prove this R-matrix Lax pair, you need so-called associative Yang-Baxter equation. Introduced by Kirillov. We will use for this construction this B-type associative Yang-Baxter equation. So this is my plan for today. Okay, let's start with elliptic function notations. So I will use odd theta function. So this is the theta function. We have the lattice of periods with periods 1 and 4. So the image part of tau is positive, and this is odd theta function, so we have this property. And we will use the Kronecker elliptic function. And it can be defined as follows. So here we have theta of sum of z and u. This is the definition for Kronecker elliptic function, and it has following quasi-periodic properties. So it is periodic when you shift by one. And when you shift by tau, you have this factor. And I will use this function. So in trigonometric and in rational limit, it goes to the sum of cotangencies and in the rational limit, it's just 1 over z plus 1 over u in rational. And I will use the Weierstrass P function. So it's elliptic function. And it's periodic. So this is the Weierstrass P function. And in trigonometric limit, it goes to 1 over okay. So this is the notation that I will use. Now I'm going to talk about Calogero-Moser system. And where is it? Okay. So the Hamiltonian of this Calogero system, classically Calogero-Moser system, is the following. So it's type a n minus 1. So we have the sum of squared momenta and the potential is given by the Strassky function, the pure coordinates. So we have the canonical Poisson bracket. And the equation of motions. So we have equations of motions in Hungarian form. This is the equations of motion. And these equations can be represented in the Lax form. So it means we have some matrix L and which satisfies an M, which satisfies Lax equation. And this pair was found by Krichever.
Yeah, QIK is QI minus QK. It's a shorthand notation. QIK is the derivative of the y plus.
QIK is correct. So this is a short notation for the difference of Q. Yes, thank you. So, and I will show you the Lax pair. It was found by Krichever in 18, I think. So, and the Lax pair for this it's the matrix. So this EIJ is just the matrix unit. And the formula for elements this is L operator. So we have here this Kronecker function phi. And I will show you how M looks. And MIG. So M is also a matrix. Here, these F are just the derivatives of phi. So this F
You meant the second term is when the I is not.
Yes, minus 1. Yes, thank you.
Actually, this notation is not very good.
What?
It's not very good notation. One minus one. Because if y is equal to 3, you have 0 divided by here.
Where?
Because qii is also 0.
Okay. Yes, maybe it's not really.
I mean, I know that it's not your notation.
Yes. Okay. But I mean that I am not equal to J. Okay. Okay. So just think that this is not the diagonal part of this.
Yeah.
Okay. So that's what I mean. And in diagonal we have this. So we have this F here. And this is the Lax pair of the elliptic Calogero.
So that's really the limit, right? When you put 0, you need to take a limit. Something like Weierstrass function. Or not.
Yes, it's like Weierstrass function plus some constant. Yes. Okay, and to prove this, you need the phi identity for this Kronecker elliptic function. So to prove this Lax equation, we need two properties for this phi. I will write down these properties. So to prove the Lax equation, we need the phi identity. And the unitarity property. So you need these identities or the derivatives of these identities. To obtain this f, you just take the derivative by qi, for example, and by u here, and obtain this Lax equation. So to prove, you need these two identities. Okay, and this story can be generalized to R-matrix case. It means that now the elements of L will be R-matrices, not functions, and it can be done using the elliptic Baxter-Belavin R matrix. And for this R matrix, there is the associative Yang-Baxter equation. And it looks like the identity, so I will put it. Well, So it's the generalization. So you can see that we have the same identity, but here we have some R matrices. This is spectral parameter, and this is quantum parameters. So this is the generalization of the Fay identity matrix generalization. And for this R matrix, there is the same property, unitarity property. Yes, okay, I will write here. And this is proportional to identity, and the same, the coefficient is the difference of Weierstrass function. So due to this generalization, you can write the Lax pair in terms of R matrices, and it was done by Levin and Shanetsky-Zotov. And I will present you the answer for this Lax pair. Yes, I will use that not really good notation, but you have already understand what it means. So here we have matrix identity matrix times P, and in non-diagonal part it's not visible. Okay, so here, yes, okay. This, instead of this function phi, we have the corresponding elliptic R matrix here. And for M, the formula
LIG are not numbers.
are not numbers now, these matrices. And by
RIJ also not.
yes, this is elliptic Baxter-Belavin R matrices. So 6 were
And they
8 vertices.
can tensor power some vector space.
Yes. So it's
So
very
I and J go from 1 to n small, and
so we have n vector. Okay, we have we have tensor product of these spaces, and Rij acts non-trivial only on Vi and Vj.
each VI is copy of Cn.
HVI, yes, is this. So
And what's the relation between n capital and small?
M capital is the so dimension of this R matrices. So in case n equals 2, it's 8 vertex R matrix. And
So
M capital equals 2, it's 8 vertex case of our matrix. So this M capital is the dimension of this R matrix, and small is the number of particles. And so
this is all related to this integrable system.
yes, so you just change this L and M, And so you write in matrix form, so you generalize, but you obtain the same equations of motion. Instead of functions, you just
For any n capital, you get the same.
yes. For any n capital, yes. It's elliptic Baxter-Belavin matrix. And so yes, and this acts this acts non-trivial on Vi, Vj. Yes. But on this huge space, it's one. So this is the future matrix. So this is the dimension. Yes. And capital is this, and we have and small is the number of these spaces. Or the
So
number
this
of
matrix R, J, they also satisfy the usual numbers.
yes.
And
And additionally, yes, with this normalization. So normalization is important for the associative Yang-Baxter. And the M is it looks like that M. So, but you have here some diagonal parts. I will write down this, or maybe not. And but here on non-diagonal you have Fij. It means the derivative of this R. So Fij, it's the derivative of corresponding R matrix.
I still don't. The upper index here, it's the coupling constant in terms of the usual numbers. Because you see here you have H bar in this idea.
This identity.
Those are-
Oh, sorry. Here is H. Here is that is H bar. So you have spectral parameters and additional parameter is quantum
But
parameter.
in this quadratic equation, this H bar is
This is
E and W.
yes. So this spectral parameter in Krichever
Oh,
is the quantum parameter in R-matrix. So this is the correspondence. And so the generalization is like this. So instead of phi, you have this elliptic R matrices. Instead of its derivative, you have these derivatives of R matrices. The spectral parameter is this quantum parameter in R matrices. So we have, and this diagonal part, yes, I write it down. It's like in non-matrix case. But we have an additional part in the matrix case. It's like this. So it's the same for all. This additional part is like this. So it's the sum over K and M of this F0. So it's
and then if you will take the Lax equation for this curly L and M, you will get the same equation.
yes, the same concept.
So you took simple Lax and you replace it by extremely complicated.
Yes, it's extremely complicated, but for example, this F, it gives you some spinching, non-trivial spinching. So when you put this Q in equilibrium positions, for example, so maybe it's not
No, but there must be some meaning on this. You probably not solving. If you're solving this equation, then there is a simple plus. Yeah, so you're making it more complicated, but there must be some reason. What is the reason?
So, for example, some applications that we have this F, and this is some after freezing, when you put this in a different position, you obtain some spin chain.
Which you wouldn't have over there.
Huh?
Which you wouldn't have over there.
Which you wouldn't. It's okay. So it's some application if you want. So maybe it's not obvious why you need to take this.
I can do this, but not so when you produce the solution, I will decide and this extension just like now you have a deal for this will be spin chain, which this is the elliptic spin chain or what?
This, yes.
Okay, so sorry.
Don't worry, it's okay. So, and my problem was to generalize this for BC case. And this model is called Calogero-Inozemtsev model. In this case, we have the following Hamiltonian. Five arbitrary constant, so this coupling constant G, which we had before. And four additional parameters. This omega is half periods. So here is 0, just like this. This is and the equation are the following. Yes.
In constraints on you,
What? I mean,
constraints on you.
no constraints. So we have 5 parameters for new, one, okay. Yes, and there is a 2n by 2n Lax pair for this. It has this structure. Block structure. Yeah, am I right that it was introduced with Takasaki, yes?
Yes.
But I understand it from your paper. Yeah, so this is the block structure and then
Actually, when I was writing the paper, I didn't know about that one, so.
okay.
Then I discovered it.
And this is the answer. Here we have this short notations. The plus and means the sum of Qi and Qj. And the blocks, these blocks have the symmetry and anti-symmetry properties. So L 1 is the minus 2 minus z. So I will not write it down. And L 2 is minus L 1. And M Yes, and I need to define this V. M has the symmetric properties, so the blocks M11 is M22 of minus Z, and M12 is M21 of minus Z. So this is the answer, the Lax pair for this Calogero-Inozemtsev model. Okay.
Who's me?
Hmm?
Who's me?
V. V is elliptic function, so this is the sum So this is V. And what are the properties to prove this Lax equation? So that two properties that we had before, the phi identity and the unitarity. Also, the unitarity property for V. I will put it down. It's like this. And the property for V and phi. It's very important to prove the Lax R matrices. So again, you need these properties and the derivatives of these properties in view. I don't want to write down this new tilde. It's some linear combinations of mu. So you need these properties to prove Lax equation. Okay. And how to generalize this for a matrix case? So again, you just replace this phi by Baxter-Belavin R matrix. It's like this. But what is V? So interesting question. What is V now? So here we have, instead of phi, we have this R, ij. Instead of this, we have R tilde ij. I will explain you later what it is. And instead of this, we have the reflection operator. So you do it the same, and here you have the same derivatives. So this is the answer. But to prove this, we need to generalize the associative Yang-Baxter equation. And what we did, we generalized the Anatoly Kirillov associative Yang-Baxter equation in B case. And add these quantum parameters. Huh? What?
This associated Yang-Baxter contain this like reflection equation.
Yeah, not reflection, I will show you. But you can obtain the reflection.
This K is some special.
So that's what I'm saying. It will add the K will actually enter Yang-Baxter or not?
The K is a reflection. So you have a KR,
Yes.
and
That's what I'm saying.
yes.
But you need some special solution or special K or special solution.
I will tell you. So now, if you understand the problem, you understand. I hope you understand what is the answer. So not in details, but I will talk about this associative Yang-Baxter equation in B case.
The reflection equation is the usual reflection equation.
I will put it down.
So look at associative equation, which will apply.
As consequence, it would be kind of reflection equation. Even not this.
So, talk about this associative Yang-Baxter equation. So if you remember, we have this for R matrices. So but I put this for AN type. So the associative Yang-Baxter equation is just this. And when you add for this the antisymmetry, so this looks like half of the classical Yang-Baxter equation. Yes, and when you add the antisymmetry property, you simply obtain the classical Yang-Baxter equation for this. And you have also this commutativity relation, almost commutativity relation for different I, J, K, and for distinct. And what I wrote down before, it was a generalization. So here we have some quantum parameters and spectral parameters. And it was quantum elliptic Baxter R matrices. And for BC case, this following Kirillov, this associative Yang-Baxter equation is the following. So you have now Rij goes like in A case, you have some R tilde. And it's symmetric. You have these obvious relations. So we commute with distinct KLij, all R with R tilde. So I don't want to write them. You have these three terms relations. And now there are three additional relations with R and R tilde. So the first one is for A case, and the other is mix R with R tildes. So for this relation, so I will write it down. Just to understand what is this associative Yang-Baxter equation is. And you have this another relation. So you have this Y. It's like it will be this K in the reflection. And this is the B type associative Yang-Baxter equation. And how to generalize this? So you can do the following. So we did it for the Shibukov-Yen operators. So I will write it down. So this quantum R matrices, they can be presented in the following form. This is the form of Shibukov-Yan operators. So these operators, they satisfies, so this S is just the permutation, so it acts now on functions, and it permutes xi and xj. And these operators satisfy the quantum Yang-Baxter equation and the associative Yang-Baxter equation. So the same that I wrote before with this spectral parameter and this quantum parameter. Okay, and Yuki and Komori-Hikami proposed the boundary K operator that can written in terms of that function V that we had in a Lax pair. And this T is just it acts on functions and it's changed the sign before xi. So it gives f this is x. And Komori-Hikami proved that this R and this K, they satisfy the reflection equation. So written in this form. So you asked me about the reflection. So this here it is. But we will use in our Lax pair.
This R-matrix is unitary.
Yes. And the same unitarity that we
Okay.
and this K also satisfies the unitarity property, like V. Like
This is related in any way to learn.
yes. Yes,
Okay.
it's two ways.
It's just a different.
This procedure is called Pasquier. Pasquier proposed the procedure how to obtain from this Shibukov-Yan operator the elliptic Baxter. Yes, and what I need else, so I need this R tilde. R tilde now is this operator. You conjugate by this T, and we will use not this K from Komori-Hikami, not this, but K tilde, and it's connected with K like this. I And in this Lax pair, in the Kawasaki Lax pair, you just take V, put K instead V, put R tilde instead of phi, depending on sum of parameters. So this is the answer. And it appears that this R tilde, this K tilde, and this R generalize these Kirillov identities for associative Yang-Baxter equation, but you need to add some parameters here, yes? So the spectral parameter and the quantum parameters. And to finish, yes, just to finish, I will put down the most interesting this four-term relation in terms of K and R. So, for example, to generalize that last term four-term relation, just do it like this. So if you put this Shabukovian operator, this R tilde, this K, you obtain the right relation. And this is
The quadratic at least.
oh, sorry. Not quadratic. It's not it. And maybe it reminds you that property for V and F,
So only one K is out.
I guess, quadratic. All K with tilde, and this quadratic, yes. So four terms like this. We have here R, Y, R without tilde, R, and then two with R tilde and K. Yes, so this is the generalization. If you put this operator, so it's satisfied. And this reminds you the identity with V and phi that I wrote down to prove the Lax pair in this case.
Right, but there's only one R tilde on the right. There's two R tildes, right? Yes.
Thank you very much. Yes, I don't have one. So I finish. I stop here. Thank you.
Any question?
Can I ask a very impolite question? What is the main result?
The main result is the generalization of this associative Yang-Baxter in the case. And
Sorry, say it again. What is the main result?
so which generalization when you put this
I have some questions. You wrote many solutions to the Yang-Baxter equations. Does this corresponding matrices are unitary or not?
Yes. Unitary, yes.
Unitary, yes,
Yes.
always.
Yes, in this one. And so when this R-matrix Lax pair in the Kawasaki case. So we proved the Lax equation in this R-matrix form. And we have some candidates for the spin chain, but we haven't proved yet that it's executable.
And there are also you use elliptic functions for construction of solutions to Yang-Baxter equation. Does your generalization is using the elliptic function with characteristics? Because some result about elliptic Calogero-Moser can be generalized from elliptic functions to elliptic functions with characteristics. Is it this case? No?
I don't understand what is the generalization of this.
If you shift elliptic functions, for
Yeah,
example,
yeah.
sublines,
Example.
these are called elliptic functions with characteristics. Seems like you have the shifting by half periods.
Yes, but in Baxter-Belavin you have this shifted theta function. So you can just shift, for example, the arguments in phi by some not half of periods, but this things like A and so you can shift this phi. In phi, you can shift arguments, and then you obtain something that can be described in this, I think, in this theta functions with characteristics. So it's the same language, but you can just shift this in phi, or you can use this theta function. So that's you mean, I don't. Yes. Okay.
Just a comment. So with field slammers, we are doing work where you can make a cross of non-collaborators and matrices. So you can show integrability of spin chains in this kind of framework.
In this case,
Well, it will work because conceptually it doesn't matter which root system it is. It's just as long as you have solution for matrices.
yeah. So do you interpret in this and K operators in this?
No. We need someone to find solution already, like Kamori Hikami.
Okay.
Then the mechanism works. The integrability of spin chain, which you mentioned, your proposed should follow using that framework.
What do not understand which spin chains?
If you do freezing, kind of R-matrix value spin chains. So
What does it mean?
You have,
good question.
for example, higher Hamiltonians,
At
which
least
come
you can construct, yes.
from
You
higher.
can use charges, yes.
Can you diagonalize?
Oh.
Now let's go.
Maybe I ask a short question. How would you choose this Hamiltonian with this potential, being the potential Qi minus Qj and Qi plus Qj, and plus sometimes with the roots of the restaurant?
Yes, this is the way Calogero-Inozemtsev Hamiltonian.
Just
So
generalize.
It's just a remarkable fact that this particular Hamiltonian study means higher for supervision.
Yeah.
That's why there's social norms.
and so it follows from the last equation. So you have this lot.
No, in the general part, I don't know the original ones.
Oh, you mean the generalization?
Yes.
We don't generalize the Hamiltonian, only the loss. So we have this R-matrix Lax there, but we obtain the same equation of motion. So the Hamiltonian is the same.
I know the second Hamiltonian. I mean the second Hamiltonian were right.
You mean the DC?
Maybe these things.
It's invented distinct to the DC.
Mesets.
In
Meset, yeah, that's it.
In ellipticals.
maybe
It's something more than BC because we have different couple of constants to this half period.
Well, it's called BC, but it's not BC.
Yes,
But it's
something like more than BC.
So there was a discovery. But I still don't understand the species. I mean,
well, sections of.
maybe I should ask you this
Yeah.
question.
Well, ask Ivan.
Ask you one. Yes, but we need a little bit more time. Yes, we can discuss it.
Okay.
So let's have that because a bigger person tomorrow as well. I hope at least the same amount of people who come tomorrow.